Hello, các bạn online có nghe được không? Có thấy màn hình mình đang share không?
Dạ, em có thấy
Có ạ.
slide thì ạ.
Mày thấy cái màn hình mình đang chia sẻ đúng không? Ok. Hello everyone. Let's start. First of all, welcome you to the new course. It is about statistic machining. And my name is Quat. I am and will be your company when we study about these areas. Um, Of course, for this course, it is an advanced course, so some topic can be more advanced compared to machining course in undergraduate study. How about in our course? How many people already study about machining basic? Can you raise your hand? Have you studied about machining? Yes, basic machining. Okay, so there's someone never study about machining, right? You already? Ah, okay. Okay, so if you didn't have some basic understanding about machining, maybe you may spend more time to study some algorithm, basic algorithm or models. Because in this course, we just remind some basic concept, and then we will focus on some um, advanced topic, algorithm or models. But sometimes we will discuss some basic algorithm or models, for example. Okay. This is, for this course, we will have some lecture, and we may have about six lecture, and then we will have some weeks for projects. Those are for you to do something and to share with everyone in our course. So it means this course contains two main parts. One is lecture, and the other is capstone projects. Okay. Okay. If you have any question, just raise your hand or just ask the question when we are here. Otherwise, if you want to discuss more details or more advanced issue, for example, we can meet personally. And of course, you can use this email to for communication or appointment, for example. Okay, so this is the content of this course. These are the main things we will study about in this course, and we will have some advanced topic for you to study further and to share with everyone in our class. Okay, and the goal of this course is very simple. We want to help you to make a good background in machine learning in some new perspective. For example, a probabilistic view about machine learning, for example. And we hope that you can understand some main models, some main approach, and to understand some advantage, the main advantage, or some limitation of those algorithms or models, for example. Those can be helpful when you use machine learning in practice. And through the capstone projects, and we hope that you can use some tools, some existing tools or some existing models to solve some practical problems. And of course, in this area, the tools library are very popular, right? And you can easily use. And the most important thing is how to use those efficiently to solve your problem. Okay. So try to use that in your capstone project. Okay. For evaluation, these are some information. We will use capstone projects for the final for the final exam. It is considered to be the final exam. Okay, and this is the ratio about the midterm test. We plan to use multiple choice test. For this, we will have a test on a computer organized by our school. Okay, this is the plan. Okay. How about the capstone project? It will work in a group, consists of from uh, 5 to 6 students, because this course contains a large a large number of students. So each group should contain 5 or 6 students. Okay, and each group from today need to think about which topic you should choose to study. And then everyone need to do something for your capstone projects. And then some weeks later, your group need to present the content, your understanding about the topic for our class, right? And of course, you can do some algorithm in that topics to do something. For example, to solve some problem. For example, when you study about this topic may have many different libraries, right? There's some existing code, for example. You can use those to do some application or some exploration, for example, right? And of course, it could be better if you use those tools to solve some problems and do many things, right? By those words, we hope that you can use those tools efficiently. Okay. Okay. So for the capstone projects, everyone in a group are required to contribute to the main project, right? And in order to complete the projects, you need to prepare some documents. For example, your code, your program, to do experience or to do something, right? And another thing is the written report. And that is where you need to describe the topic you are studying, your understanding, and then the problem you want to solve, for example. You use these tools to solve some problem, and then the result of your evaluation, for example, implementation and evaluation, for example, right? So the report should be written carefully, right? And of course, each group will be allocated some minutes for presentation. For example, 15 minutes to summarize the topic of in your group and the results of your implementation or application, for example, right? Okay. For some reference, you can use the lecture slides or some other materials. And also, these are very good books. You have time and want to build a strong background. Those are very good. Okay, so those are all information and the way we work with this course. Do you have any question? It is okay. Everything clear? Clear? No question? Good. So let's proceed. Oh, sorry. Okay. For the group, um, for the materials, you can find from this folder. Some lectures will be here. Okay, and then the reading materials will be here. You can see those materials, those topics, and each topic will be denoted by R. Okay, for example, this this document should be in one topic, and this document is one topic. This this is another topic, for example. Okay, and in this folder, there are more than 20 topics, and those should be used for our our capstone projects. And each group we choose only one topic, and there's no overlapping between different groups, right? If this group choose this topic, if this topic is chosen by one group, then no other group can choose that topic, right? Okay, that is the constraint. How about the group? Um, okay, so let's see let's see the file. This is the initial assignments for the group. Okay, just randomly. For example, um, this should be in one group, and this should be in one group, right? For example, I denote the group index here. Do you understand the assignment? Okay, so this is group index. Okay, this is just the initial assignments, and then if your group want to change some member, then write your proposal here, the new members in your group, right? And you need to fix your group in within this week until Sunday, this Sunday, right? And then no modification is allowed later, okay? And you need, if you want to change someone, you need to have some communication between those groups, right? And then once you agree, you need to fill every members in your group, the new update here, right? For example, here, group three, with some new member, for example, okay? You will have some change. Otherwise, just just use this assignment. Yeah. Every member? Yes. Just have some positive communication if they are agreeing, for example. And then your group needs to discuss and appoint a leader and things information about the leader here, right? And then your group need to choose. Oh, sorry, there is just a Vietnamese. I will change to English later. Then your group, once formed, you need to choose one topic, right? Among those topics in this group, in this lecture, in this course. Then you need to fill here, okay? What is what is the topic your group is studying, okay? So you need to see those topics and then discuss and then choose quickly, right? Otherwise, other group can choose that and you cannot choose, okay? That's a requirement for capstone projects. Everything clear? No question? Yeah. I already provide a code to join. Then they should have some way to join. Hmm? Okay. Any more question? Okay, so if you don't have any question, let's start our lecture. Okay, before the studying about machine learning, so let's rethink about learning. What is that? What is learning? Yes, you are learning, right? You're here to learn something. It means you're learning, and of course, you learn many things uh, from the day you was born, right? And up to now, you learn a lot, and you had a lot of knowledge after learning, right? And in the future, you still learn. But it's very natural ability of your brain. Everyone here can have very good ability, right? But what is learning? What is it in your brain? It is learning, right? So what is that? How are you? Learning is something just brain how to do it again. Mm-hmm. I mean, in this sense, the problem find the function. If you learn with data, mm-hmm. And know some structure related to this problem. Mm-hmm. Okay, so the later idea about machine learning is it seems good, but the previous one you said about your learning, for example, it is still unclear. You are saying about your goal, right? To obtain some knowledge, okay, after learning. You can obtain some knowledge. But what is learning? Mhm. So the same way with him, you are saying, well, the goal, right? To obtain some knowledge. To reduce some uncertainty. Why do you need to reduce those things? Hmm. So what is learning? Yes.
When you learn when someone do something or do anything or whatever, uh, and I see that and it will be captured in my brain and I will know something about it.
Mm-hmm.
After that, I know something
Mm-hmm.
I can do that. I can do that or not do that. Try it.
Mm-hmm.
After that, I can even fail or successful. Even fail or successful, we have this is also like a quick, like a maybe like a quick,
Mm-hmm.
magnet.
Mm. Yes, something is seems reasonable, but when you're learning, what is happening in your brain? What can happen? What can be? Mm-hmm. Wow. When you're learning, you need to imagine. Mhm. Okay. Yes. It is sometimes can be difficult to say about learning. Um, but just think about our brain when we see something like this, like an image like this. When you receive a picture, you can easily understand what is inside in the picture, right? For example, in this one, what is in this picture? Yes, a cat, for example. That is easy for you, right? To to see or to observe or to categorize something or to understand something. For example, there is a chair and it is something else, right? So it means that when you see a picture or you see something, your brain can easily understand, right? But how does your brain do something like this? You can easily recognize something in a picture or easily understand the meaning, what is inside one picture, for example, right? So how your brain can do something like this? Yes. So it means that when we receive this picture, right, or this one, when we see this picture, your brain receives some signal, receive a picture, right? through your eye, for example. So your brain will receive some signals, some observation, right? And then it can do something else to process the signal, to process the input. And then after doing something else, it can provide an output. For example, you know that it is a cat, right? For example, yes, your brain produces cat, for example, or something else here, a chair, for example. So when it receives some signal from the environment, right? So your brain do something else and provide some other things. So what it is doing, and you can see that it seems to do a mapping. That is, it connects one things, one input to one output, right? And it is very common for our brain. Let's think about your brain, how it can work. And you can see this, right? Okay. But one question is, because here it is doing some mapping, it means that your brain already have a map, some map, right? To connect this one to that one, for example. And the question is, where does the mapping come from? And before that, let's remind about a mapping. What is a mapping? It is a concept in math, right? In fact, we can consider that to be a function that can connect one input um, to one output, right? For example, we denote by the function to be f, it connects from x to y. X here, we can consider that to be some observation, some input signal, right? For example, the picture in one image, and then your brain produce cat. That is output, right? For example. Okay, this is function or mapping. So a function can map from the input to another output, right? And in fact, it is working on, we can consider that to work between two space. One space is the input space, right? And the other space is the output space. Because sometimes if the input is here, the output should be here, for example, right? So it can connect many points in the input, many points in the output. Okay, how about your brain? When it receives some observation, X, right? Then it uses the internal mapping to produce one output Y. But here, we do not know what is the mapping, the internal mapping, right? The hidden mapping. It is hidden in your brain. You may not know. Anyone know? You know? Yes, of course. No one knows. What is it? It's a hidden mapping inside your brain, for example, right? Okay. So by this way, you can see that because you can understand many things in practice, right? So it means that in your brain can contain a lot of mapping. And one question is, where does the mapping come from? Or in other words, how your brain can find those mapping? Because it means that, right? You use many mapping in daily life. So where the mapping come from? Yes, you discussed before, right? So what's that? Where? How how can you have some mapping like that? Mhm. Only receive, and then okay. In order to understand one picture or one sentence, you need a lot of knowledge, right? And how and where does knowledge come from? Can a baby understand this picture? For example, 1 month baby, can she understand this picture? Maybe no, right? Because she may not have good knowledge, right? It means that she has not go through a training process or learning process, or learning periods, for example. In order to understand this picture, or in order to understand some sentence in this slide, you need to learn a lot of things before, right? Otherwise, you may not understand anything. Okay, so the hidden mapping in our brain can come from the learning process, some learning processes, right? Or sometimes memorizing something. Okay, so in practice, we can learn from some example in practice, right? For example, you observe many things, and then you know that each one should be this, and that one should be like that. This is cat, or that is dog, for example, right? You observe many things in the past, and then your brain can understand, can do some process, internal process, and then it can produce a mapping from a picture to the output, for example, right? So in practice, you can learn from a set of example. Sometimes the example can have some label, right? For example, in the past, you may see some picture like this, and this picture, someone already said that these are cats. So you can understand these are cats, but this is not the cat, for example. And this is a chair, for example, right? So in the past, you may um, learn from some example. Sometimes each example can have some label, right? For example, this is a label, okay? But sometimes you may learn from something without any label, right? So those observations is come from the input, right? In practice, we can observe something about the input, and sometimes we can observe about the output. And those should be example for you for to learn something, right? To understand something. And of course, to find some hidden mapping, right? And and once we have this hidden mapping, you can use us for future practice. For example, in the previous example, um, you already have this that mapping. Okay, now let's make a prediction for this picture. What is inside this picture? It is a cat, a dog, or something else? So it means that once you have some mapping, right? Once you have some knowledge, you will use your knowledge to do some prediction or to do some inference, right? And of course, in practice, for one thing, for one concept, each one may have different understanding, right? Sometimes we can understand this to contain a dog, but another one can understand this to contain a cat, for example, right? But each one may have different knowledge, right? And it means that your knowledge can be very different from the reality, the real mapping, for example. For example, there exists a real mapping from these pictures uh, to one output, right? And that mapping, the truth, may be very complex, very hard to know, right? And maybe we never know. We never know the truth. And what in your knowledge, you are using another mapping, right? You are using another mapping to map from X to Y. And your knowledge can be very different from the truth, right? Do you have any, do you have, can you find the truth in your brain? Okay, so those examples and connection to your brain, and I hope that those can help us to understand what is learning, okay? So that's why in machine learning, when we say it's about learning, it's often talking about some mapping, as you said before, right? We need to identify the fundamental things when we saying about learning or something else, right? Okay, so what is the learning problems? In general, we can consider that to be to find an unknown function. We denote by y star that connects from x to y. We need to find this function based on a data set D. That's all. Very simple. And this data set should be collected in the past, right? By some way, you can collect some example about X and Y, for example, right? And all of those, we compose a data set. Sometimes we call that the training set, right? And of course, those training set always have some few examples, not infinite, right? Is there any problem that D can contain infinite number of examples? We never have. We never have. We face with that problem, right? Because everything up to now you learn, the number of example or the number of observation up to now may be finite, right? Okay, so in this case, this function can be considered to be the truth or the ground truth or the reality, right? And the learning problem is to find this function. Okay, but in jailbreak, we may never know this function, right? And your knowledge can be close to the truth. In this case, you already learn very well, right? So your knowledge or your mapping can be very close to the truth. Or in other words, you are using one function, one specific function to approximate the truth, right? In your brain, you are using something to approximate the truth. Okay, just correct me if I'm wrong. Okay, don't worry. Sometimes maybe I will be wrong. So the learning problem is very simple. The statement is very simple, but it is not simple, right? In order to find the truth, it is intractable, right? In practice, we cannot hope that we can find exactly this function, right? So that's why in machine learning we often approximate that. And there are two main problems in machine learning. One is supervised learning, and the other is unsupervised learning, right? In the case, if we observe the output correspond to the inputs, right? And the training set should contain some pair, for example. So in that case, the learning problem is supervised learning because there's some supervision here, right? We already know some output. But in the case, if the training set do not have any label, so we'll work with unsupervised learning. Those are very basic. Okay, and of course, for supervised learning, there's some sub-problem. For example, sometimes you can work with regression, or sometimes you can work with classification, right? In the case, the output can be a number, a real number, for example, right? So in that case, you can work with regression problem. But when the output can be discrete, it belongs to a discrete set. For example, it only receive one of those two values, for example, right? So in this case, you may work with a classification problem, right? So the output space is finite, right? And of course, for classification problems, sometimes you can work with a different problem, sometimes binary, sometimes multi-class, and sometimes multi-label, right? That is, the output can contain some label from the output space, for example. So in that case, your problem is multi-label, right? Okay. And of course, up to now, we may have many more problems that also belong to supervised learning. For example, want to learn a mapping from a sequence to another sequence, for example, right? For example, if you train models, train a system to do translation, for example. The input is one English and the other is the output is French, for example, right? And sometimes text to image, for example. This is text and this is image, for example, and image to text or many other problems up to now, okay? And of course, many system AI system now often trained by supervision, like this, right? Okay. Any question?
Em chào thầy ạ.
Yes.
Sorry. So in this class, I joined the class late, so I don't know. Should I speak to you by English or can I speak to you in Vietnamese in this discussion?
English, please.
Okay. So far, from the materials, I see that you have mentioned the like the two main importance about the supervised learning. Uh, in this from this step, will we know about the way we split the data to perform the training or like the classification, even with the regression?
Sorry, it's still unclear to me. Well, what is the question?
Yes. So far, I see that we have reached to the two main problem, to the
Yes.
two main problems of the supervised learning, which
Yes.
is
Uh-huh.
classifications and regressions. Uh, I also interested in about the way the data will be used to feed to the problems about splitting the data for the problems. So will we know about the splitting method in the later discussion?
What it means about splitting the data?
Okay, so I understand that in machine learning, data should be used for training and testing. That is what I have known for a
Mhm.
while, but
Yeah.
the exact process to split the data, like the correct amount of data to be splitted. For example, like we have, I usually see the 80-20, like 80 for training and 20 for testing. I only know about the number, but I don't know the exactly the exact how would I say, like the exact method. Why would they split like that? That is what
Uh,
I want to know more.
okay. So your question is about evaluation, right?
Yes, sir. Yes, sir.
Okay. So after training, you want to see the quality of your models or your system, right? So in that case, you need to do evaluation. Okay. So if you want to know more about evaluation, I suggest you to read some basic book or lectures about that, because in this lecture we assume that those basic understanding should be present for every student. Um, Later, I will send you some videos or some materials to study about evaluation. Okay,
Thank you,
that's
sir.
one
Thank you
lecture.
for your answer. Thank you.
Yes,
Yes.
one lecture about model selection and evaluation. That
Okay.
is very basic.
Thank you, sir.
Okay, any more question? Okay, so let's discuss more about supervised learning. Okay, as we said before, for for these problems, there is an unknown function, right? That can map from x to y, from input to output. We denote by y star. And the x here, we we call that the input. Y is the output, right? And this unknown function, sometimes we we call that the labeling function. Sometimes, okay. This is just one example. This is the function, the unknown function, okay. And in practice, because that function is unknown, but sometimes we can collect some example, some data sum that related to this function. For example, we can collect x1 about x, y1 is the corresponding output for x1, for example, right? Sometimes we can collect this pair, or this pair. For example, here, those points in this area, we can collect some example, okay? But every other part may not be known, right? And our task is to learn or to find find that function based on the observed sample. That is a supervised learning, right? Okay. Let's discuss about the data. It depends on the situation or problems. Those data can come from different mechanisms, right? For example, for one problem, you can collect some example by yourself, but the other one can have some other way to collect the data, for example, right? So consider that to be generated by some process. Each example can appear by some process, can be produced by some process, right? And that process, sometimes we call that a distribution, probability distribution. And of course, this distribution, sometimes we may not know, right? And this one, sometimes we say that it is the data generation model, the way we generate the data, right? But in practice, we may not know exactly what is that. What is that model? What is that distribution? Okay? For example, sometimes your distribution can be very complex like this. In practice, you only collect some sample from that distribution, right? Just so those examples can provide something about the true data distribution, okay? And the associated label. And in order to easily work with some algorithm or to analyze some properties, for example, sometimes we can assume those examples to be II, independent, and generated by the same distribution. Okay, so for that learning problems, you know that what you only know is the data set with finite number of examples, right? There's two unknown, the data distribution and the labeling function, right? Those are two unknown for your problem. And the learning task is to find the unknown function, the labeling function. And of course, it can be impossible to find that function, right? So that's why in machine learning, one approach is we use one specific function to approximate the truth. And that specific function should be easy to work with in practice. What is the idea in machine learning? For example, your unknown function might be like this, but it might be complex. Okay. Now, you use another function that can be easy to work with. For example, with this function, with a very simple shape. And this function can be easily work or create or something else, right? And you are trying to use this to approximate our unknown function, right? You are trying to use this function to approximate the truth for everything. Okay. That is the idea in the and this function, sometimes we call that a predictive, or sometimes after training, you can call that a trained model. Sometimes, okay. But how to find that function? You need to use some learning algorithm, right? Sometimes we call that a learner What is a learning algorithm? It is a method that can produce one specific predictors based on a training set D, right? That means that this algorithm receive one training set and then produce one predictor, right? That is a learner, very simple like this. And we can consider one algorithm to be a mapper, right? It can map from one data set to one predictor. Okay, so that is a learner, very simple. And one question is, because a learning algorithm can be considered to be a mapping, so it is working with some space, right? What are those space? It map from one space to another space, right? So what are those spaces? For example, in maybe you already know some algorithm like least square, Lazo, to train a linear model, right? Those are learner or KNN reasoning also, right? Those are very simple learners. And of course, in practice, the learner may never know the truth, right? The true labeling function and the true data distribution. It may never know. Even for me, for you, for example, you build something, but you never know this, right? Okay, so let's return to this question. Do you have any answer? Yes? Any?
But on
Mm-hmm.
a training aspect,
Mm-hmm. Mm-hmm. Yeah, that's right. It marked from something like data space to um, the model space. What is the data space here?
somehow we can call this X. This is a data space. It is a product of the input space and the label space, right? And in this space, sometimes we will pull out the data space. But here, one language will receive some example in the data space, right? So one example, X, Y, should be one example from the data space, right? And now our data can contain the size of our data is F, right? The training set contains M example. So essentially, you can write that D to be a subset of D N. Finally, it is D multiplied with D and multiply and count. Okay. So by this way, you can write an algorithm. It is a mapping from V n to 8. And receive a data set and then produce one prediction, right? Okay. So one training algorithm, we work with two different states, right? The model states. Sometimes we formulate the model state. It contains every possible model we are working with. Sometimes we say that it is hypothesis space. Okay. What is a model space? Sometimes we call that the hypothesis space. As we know, if we want to solve the learning problems, one idea is we use a simple function to approximate the truth, right? For example, like this. We use this function to approximate the truth. But what is the space for this function? So A to be belong to some order space, for example, right? Okay, so in practice, we need to restrict the space that we are trying to explore, right? To explore a good predicate. So that space, sometimes we denote by it, and sometimes we say that it is a hypothesis space. For example, this area. These areas contain all possible functions once we restrict our subspace. And the learners are trying to find one specific member in this space in order to approximate the unknown function here, right? For example, the unknown function can lie here, but our model space can be this area, right? And the learning task is to find one specific function in H that approximates the truth. So it depends on the choice. Sometimes you can choose some small or simple function to approximate the truth, right? For example, you use some hyperplane or linear function to approximate the truth. But sometimes you can use a very complex function like this to approximate the truth, right? So that is your choice. So this set or this family depends on your choice, right? But how to choose the type of function to approximate the truth? About the theory?
Nice. And I'm working on working on some like
The question is, in your experience, how to choose this moral state?
means when the problem with the hypothesis by understanding the knowledge of experiments, I will just see that in this experiment
have some like like something about the corresponding to the something. How are you? What is your experience with first of all, I think check the tradition. This that and some of the language but how to choose the moral state? Or in other words, how to choose the moral part, moral architecture? Yes, I want to ask. Based on the output, I want to task it. Like the binary classification or multi monthly classification or answering problem by that we choose of time. Yeah, of course, we need to make renewable and everything. Because even for one problem, we can choose. We can have many choices, right? So how do you have that one good? Which for more time, more okay. After basically, we also have like the specific time model of to show specific problem. But in real life, I usually like the experiment first. So I recommend to see like the big algorithm to the problem I want to solve. So the way is to do empirical. Define some type, some model type, and then observe the performance, right? Okay. Yeah, that's it. Thank you. Okay. So the model state in practice, sometimes you call that model architecture. You choose one architecture, sometimes linear, sometimes a neural network, or sometimes a decision tree, for example, right? Those are different types of model state. Okay, so for the model state, it contains a lot of functions, right? And each function can map from one input to one output. And of course, in order to choose a good model state, it depends on your knowledge, prior knowledge, your experience, right? After doing many tasks, using many model types, for example, in the past, then you can get some knowledge. Which one can be good, or which one can be very bad, for example, right? And your experience can be helpful when you face with new problems, for example. Okay. So the choice about this space depends on your prior knowledge, right? And well, this it means that this space can reflect some bias, some of your bias, right? And sometimes here we say that it is inductive part of preference, right? It encodes your preference about the model. Okay, this is just one example. Sometimes we use a very simple function, and it means that the model space is very simple. It contains a lot of linear functions like this, right? And this is just one example for linear model. Okay. Any question?
Okay, so when we work with a learning problems, um, one of the first step is to choose the model type, right? Sometimes we use a linear model or linear type in a function, for example. Sometimes you can choose a more complex one, for example, right? Once you choose that, inside one hypothesis space, in one model space, there are many different characters, right? So which one a learner can choose and how it can choose? Because the model space here is very large, right? Sometimes it is very large, infinite, for example, right? How the learners can choose a good one? Similarity. But the ground truth, we do not know. How can you compare the similarity? Yes, you say about similarity. Essentially, it's a, we are trying to do something like this, but you need some a principal way to see the goodness of each function, right? Because in the model families, there are infinite number of functions. Okay, in order to choose a good one, you need some way to see the quality of that function, right? We're going to make some prediction. What is the quality? So in machine learning, we use some other function to measure the quality of each prediction and every prediction, for example. And that function we often call a loss function or sometimes a cost. Okay, so a loss function are trying to measure the difference between the truth and the prediction. That's all. So any function that can prove that can help you to see the difference, right? And of course, that function can help you to see the quality of each prediction, right? And in practice, in machine learning, there are many different laws. For example, 0-1 laws. That is very, very popular. For example, for one prediction, it is different from the truth, then the loss should return 1. Otherwise, it will return 0. If the prediction is correct, then 0, 0. The loss is 0, 0. That's all, right? And of course, in practice, we often use the accuracy, right? The accuracy, it is the inverse of 0-1 loss. But that loss can be difficult to work with for learners. So in these areas, we can use some other type function. For example, square loss, like this, or absolute loss, or sometimes hidden loss. And when the output are some vector, then we can modify those loss to with vectors. For example, you use L1 norm or L2 norm square, for example. We can use those to be the loss to see the quality of each prediction. Okay? And based on that, you can measure the quality on average, right? We use one function or one prediction to make prediction for every example in our data set, for example, right? So what is the quality? One way is just take the average loss on that data, right? And that quantities can be written by this, and sometimes we call this the empirical loss, or sometimes empirical risk, right? This is the average error on a data set, right? In the case, if we want to compute the average of the error over the whole space, for example, then this is how we need to compute, for example. We compute the expectation over the whole space. And these quantities, it is often known as expected risk or expected loss, right? And this is the quantities we want to know in order to see the quality of one function, right? One predicate. We need to measure this, the error on average, right? Average over the whole space, the whole data space. And these quantities, sometimes it is similar with the errors we often use in practice. The accuracy, for example, the inverse of the accuracy. For example, for binary classification, we can easily show that these quantities, the expected loss, it is in fact represent the probability that one prediction can be incorrect. So this is the error you often measure in practice, right? That is interesting. Okay, any question? Okay. So let's return to the learner. The learner is want to find a good function, right? Once we choose a model type or a model family like this, and one training set, right? The learners need to find one specific function, one specific member in this space in order to approximate the truth, right? That is the learner's task. So the learning goal is we want to find one specific function H that have very small spatial loss, right? And that function can generalize well. It means that the error for future prediction can be small. And in that case, we say that model can generalize well on unseen data. And that probably should be very important for machine learning and AI now, right? So ultimately, we want to find the best function in the model family so that it has the smallest expected loss, right? That's all. That is a learning goal. And that learning goal can be formulated as one optimization problem like this. We are trying to find one argument that minimizes this expected loss among many functions in a model family, right? The learning problem can be translated into one optimization problem. That's very, very, very common way in this area. And of course, this objective is very different from another concept. It is fitting in mathematics, for example. For fitting, learning is very different from fitting. Sometimes for fitting, sometimes we mostly focus on the training sample. We're trying to minimize the error when we fit one function on a given data set, for example. That is fitting. Okay? But here we want to learn a good function that generalize well. It can perform good prediction for future observation, right? That is very important in machine learning. Okay, but in practice, the expected loss cannot be computed directly, right? Because this is the expectation over the whole data space. And we cannot access everything in the data space, right? So that's why we cannot access to this function. And one way to avoid this is to focus on the error on the training set. That's a very, very simple way, right? And it means that if we focus on this, you are trying to minimize the learning error, or you are minimizing the training error. That's all. That's all. And by this way, sometimes it is known as empirical risk minimization. This is a very classical way to help you to train the model. Okay? And of course, by this way, the trained model can be outfitted, right? Because it is just focused on the training data, but forget future, for example. So, outfitting my clear. And of course, in the case, if we have a huge training data, for example, these methods can be good, right? Because of the law of large number, right? You know that this average when goes to this expected number, right? When the number of sample or the training size increase to infinity, for example. So in the case, if we have a large data set, for example, so this method can be good. But in the case, if we have a very small data set, these methods can be very problematic. So be careful about that. Any question? Everything clear? Great. So we should have some minutes break. Okay, 10 minutes. Okay. So let's continue. Okay. So let's remind a very simple models in machine learning. It is the linear models, and we will remind about linear regression. Okay. For regressions, the main task is to find one unknown function based on a training set, right? And of course, for this problem, the output can be a number, a real number. So this learning problem is regression. Okay. Okay. The first step is we need to choose a model type, right? There are many choices, but now we choose a very simple choice. It is a linear model. That is, each function in that model space can be a linear form, right? For example, like this, we will use a function like this to approximate the unknown function, right? And we denote by f, x, w with this form. And here, the input, x is the input, and w is the weight of the function. And sometimes we call that the regression coefficient, right? And sometimes we call them to be the weight, right? And W0 here, sometimes we call that the bias of the model. So if we choose this model, it means that we have one assumption. The unknown function can be simple and can be well approximated by a linear function, right? That is our implicit assumption. But in practice, that assumption sometimes wrong, right? Sometimes good, sometimes wrong. Okay. And assume that we choose this as this type of model. And of course, this function depends on two variables. One is the input x and the other is w, right? Those are two variables of this function. And of course, it is not linear with respect to the input, right? When we consider x to be the variables, so this function is not linear. But when we consider w to be variable, this function is linear. So that's why we call that linear model, right? And of course, once we choose a model family like this, of this form, even for this form, there are many linear functions, right? And our task is, the learning task is to find one specific linear function based on a given training set, right? And for this type of function, in fact, we are trying to find the weight vector. That's all. That's for the linear model, right? Okay. So in order to learn a specific function, we first define a loss, right? We define the loss based on the training set, and we call that the empirical loss. Okay, let's define. We denote by R at S to be the sum of square error for the example in the training set. And in this case, we are using square loss, right? And for linear models, we can write explicitly like this. If we divide this by m, so we can recover the empirical loss, right? But this quantity, it is only the residual sum of square. So we can know that this quantities, it is an approximation to the true loss, the true error, right? The expected error. And the gap between these two, sometimes we call that generalization error. Okay? And when we train the models, we hope that this gap, this error should be small as possible, right? And in that case, our model can generalize well. Okay, so once we verify these quantities, the idea for training is very simple. We can minimize this, right? That is, we will find one specific linear function that minimizes this error, sum square error, right? By that way, it is known as ordinary least square, right? OLS. The idea is just minimize the training error. Or in other words, we are trying to find the weight vectors that minimizes sum of square. That's all, right? Very simple. And for this problem, we can solve this problem very simple. For example, we can take the gradient and then we can solve this equation, right? And then after some manipulation, we can arrive at the optimal solution like this. So this is the first algorithm. The first learners, very simple learner, apply to linear models for regression, right? The idea is very simple. Just minimize the sum of square error. Or in other words, it is trying to minimize the training error, right? That's all. And of course, we can summarize the algorithm to be like this. The input is one training set. Then in the training phase, we just compute the weight vector to be like this, right? And that's all. And after training, we already have one function that is ready to make prediction, right? That's all. And for some data set, these methods can work very well. For example, in this case, we have one data set with the inputs here and output here and inputs here like this. And after using OLS, after training, we can obtain one specific function, f star, like this, right? And when we draw that function and plot the training points like this, and you can see that the trained models can approximate those points pretty well. That means that this function, this trained model can be good, right? Okay, so OLS, it is one learner. It is very simple, right? Natural, but it has many limitations. For example, in this linear regression, for example, when this matrix is not invertible, so the optimization may be more difficult because we cannot solve for the solution directly, right? And sometimes it can be expensive if we try that way, right? And more seriously, these methods can be overfitted because we just focus on the training error, right? Okay, so this is just one example for one problem, one learning problems, and one learner, and one model. Any question? Okay. So here we have one example. When we have a simple learner, if that learner just focus on the training error, so overfitting might appear. What is overfitting? You know? Yes? Kulang?
Uh, yes, so overfitting here is the process where a model can do really well on a trained data set, but perform like very poorly on a test data set, like in the real life data set. That is what I understand about overfitting.
Mm-hmm. Yes, correct. Overfitting. The model can have very small error on a training set, but can have very large error for future prediction, right? So in that case, our model can be overfitting. Okay, so it means that in practice, we need some way to avoid that situation, right? Otherwise, your system can be useless. The prediction should be inaccurate, right? Wrong, very often, for example. How to avoid this? We need some way to do rewriting, okay? In practice, for one problems, you will have many choices for the model family, right? Sometimes even choose linear models, sometimes even choose decision tree, for example, but sometimes even choose a neural network, for example, right? So many choice for the model type, right? And each model type can have different properties. For example, a linear function. It is very simple, right? Like this, very simple function like this. It is ability to approximate the two function. It should be very hard, right? But sometimes you choose very complex model. Sometimes. So for this family, it is very complex, very strong. And then it can approximate any training example in your training set. So in that way, the training area can be easily to be small, right? But for that models, the test error can be high, even though the training error can be small. If we choose more and more complex models, this situation might appear more frequent, especially in the case your training process is very, very bad, for example, right? Okay, so we need to avoid this. But why? What what can be happens in a case if we choose very complex model, or sometimes we can choose very simple models? When overfitting may appear, and when other situation may appear, for example, and how the error can be seen or can be understand clearly. For example, if we understand the causes for the error, then we can have some way to avoid to reduce the error, right? So that's why previously there's some decomposition about the error in order to help us to understand more what can cause a high error for models. Okay. It is a bias Darren decomposition. To see this, let's take one example. We consider a regression problem with the unknown function to be y-x. It is composed from the truth and another things we call the noise. Okay, and the noise here, let's consider a very simple case. It is the white noise. That is, for each prediction, it is added by a random noise, S1, for example, right? So S1 here represents some noise or some error in measurement, for example. Okay, after training, we can obtain one specific model, right? We denote by F hat. And of course, it is a regression. We can use this to approximate Y star, right? But because we train this model from a data set, for example, we train from D, a data set D, for example. So it means that the trained model depends on D, right? And we write this to emphasize that, okay? And in practice, we hope that the trained model can approximate the truth very well, right? But in practice, our models can be a random quantity because the data set, the training set can have some randomness, right? For example, you can collect a data set by yourself that is very different from the data set by the other one, right? So the training set can be very different, even for the same problem. There's some randomness in the training set, right? The way we do sampling, or there's some other thing, noise, error, for example, right? Okay, so train models can be considered to be random. So sometimes we can obtain this model, sometimes we can obtain another model, right? And those can be very different. So for each model, we can measure the error, right? For example, if we use a square error, this is the error for one prediction. But here we have a random quantity. Our model is random, right? So only one value do not say anything about the quality of that model. We need to take the average, right? The average over the whole data space. It is normal, right? It is common. But this is not enough to understand about the error, because our train model there's some randomness in our train models. So one way is to consider the learning algorithm that produce the train model, right? And then we can take the average over the every training set as possible. And also we take the average over the whole noises, for example, right? We consider on average, what is the error? Okay. And then we denote by error of A at one input X. Given one input X, what is the average error of algorithm A, for example, right? So, but this way, these quantities should not depend on some randomness in the noise or the sampling, right? And should be more reliable to analyze the error. Okay. And from this expectation, we can express this expectation in more details. And then, fortunately, we can decompose that into the sum of three different quantities. The first quantity is the variance of the noise. And the second quantity, it is the square of bias. And the last one is variance. What is the bias? Here is the bias. The difference between the truth, the ground truth, and the prediction. The difference, and we say that's the bias. Sometimes we call it the error, right? And the variance essentially says about how much each prediction by the algorithm may vary around the mean. This is the mean of the prediction. This is one prediction, right? And when we take the expectation over the whole training set, every training set as possible, right? We take the average because each data set will produce one function, another data set can produce another function, right? Then we take average overall. Okay. So we can see that the error of a prediction can be decomposed into the sum of three different non-negative numbers, right? If we want to minimize the error, what are we trying to do? We need to try and we need to reduce both, right? Both bias and variance. Okay, so let's consider some situation in practice you may face. For example, this is the ground truth. Okay, this center, it is the ground truth, but your algorithm always produce some fraction something in this area. So on average, this fraction very far from the ground truth, right? So in this case, the bias should be high. And the model should be very, very bad, right? The trade model should be very, very bad. But the prediction from the algorithm concentrate in a very small area. That is the variance, the deviation from those predictions to the mean is very small, right? So in this case, the algorithm can have a high bias at low variance. It has very consistent prediction, but overall, the prediction is very, very bad, right? That is one situation. So in this case, what happened with the model, with the trained model? What happened in this case for the trained model? Overfitting? Okay, so let's consider another situation. Sometimes the prediction from the algorithm diverges like this. Sometimes here. Okay, so the prediction spread in a large area, right? So it means that on average, those predictions can be very diverse, right? And the variance overall should be high. And of course, those predictions is also very far from the ground truth, right? That means that in this case, the algorithm can have a high bias and high variance, right? And of course, in this case, the prediction is inconsistent, right? And the trained model can be very bad. And sometimes you can face with this situation. The predictions can be very diverse, but the average is very close to the ground truth, for example. What is the prediction just stay around the ground truth, right? So in this case, the prediction can be inconsistent, but on average, it is good, right? So in this case, it may have a low bias, but high bias. How about in this case, it is good? How about the trend model? It is good in this case. Sure. Can you explain why? More general? What it means about more general? Mm-hmm. So in this case, you say that the trend model should be more just general. Can you explain what it means about general? What it means and generalization, right? Yeah. Generalize. This actually is only for one input act. Why you say that the model can cover different scenarios? If I think for only one act, right? One input. Okay, so for this situation, the trade model should be bad, right? This also is bad. How about this statement? Good. Yes, can I have this? Let me give different discipline. This is for the week. I mean, different discipline happen. The model happen, low one happen. If we fit very good, that is true. We will understand. Or actually, between time and exactly to bring that model to happen for the future. And if how can I say that it is good for business? Because the value is defined by this principle. It is expectation of the whole value things that because the expectation in the very each for the expectation here. It's a equally for the whole space on the effect, not for the just one. So for the data set in the future, for the data not the set in the future, that is not that actually in fact not but actually the whole for the whole space. That's why we have to take it. And so that indeed with the domain here, it just means that we see the ground truth here with one star minus for the for this data set, and if it's low, expectation of the expectation here nothing for the whole screen for all the data for the it's very small. So that means on the here. But actually for the future data,
we have expectation in the values. I mean, for the whole thing, that's not the whole thing of the model that we already seen in the past. One about in this case, what can happen? Very model.
I think in this particular meeting, I have the whole thing.
How many?
The model.
How many cities do that?
We can see that the sound of the arrow in the elevator to accelerator by aspect the program. In this situation, the program is between the different data, the subset of the data space. So when we train the subset of data set, will performance of the model will be trained different. So we can in the exact the model the actual well on the quantity the set data set that become the sensitive and we send the
Anyone understand it? Really, in this case, I'm living human beings, right? Yes. How about in this case, calculating or other things? Well, I can really see that, how about this thing? How fitting or other things? I think I think but the outcome is operate so yeah, I like this one. So in this situation, on this one, the definition of the question is high. So it suggests that the training model can vary a lot depending on the training data, training set. One point here corresponds to question from one model. Another one can come from another model, right? And each model is the result of one training set. This is from one training set, and this from another training set, right? So the good like meet that the output of your road can have it can vary. So it means about the trade one is easily overtake the finish. And when it has a non-infinite data, you train data for that. The noise can cause. The moment you move a lot, right? Especially for running with that. So in this case, a lot of models might be updated. And also in this case, a lot of trade models may be updated. But account for unbelievable and unbelievable. Right? How about in this case? Most models may be unbelievable. Right? What is unbelievable? There is a number. So you know, on the But okay, so in this case, are we or other people? Yeah, that's right. The fraction of different models is about very small, and that can be very far from the truth. About thinking of the level of family or family fraction can be that, right? And the fraction from the different models is around 1 small. So, I'm going to almost gone. So the case of really, right? Almost really more. How about this? When there's low breath, we can easily train a good mark, right? It can generate breath. In this case, right? So in my case, we hope to work in this situation, right? Low bias and low variance. That is, most models can be easily trained to be good. Just few can be hard to train. Sometimes overfit and sometimes underfit, right? So from that understanding, you can see that in order to reduce the error for each fraction, both quantities should be small, right? Bias and variance should be small. Okay, but in practice, if you want to decrease the bias, how can you decrease? That is, you want to have a small bias. So in that case, your model should be strong enough, right, to approximate the ground truth. Especially in the case the ground truth is complex, then the model should be strong or complex enough, right? So in that case, you can hope that the bias can be small. So one way is to increase the model complexity. You choose another model family that is more complex, right? Instead of linear, you choose a neural network, for example. But when you increase the model complexity, the variance tends to increase. You see why? Can you see why? If we increase the model complexity, it will change to more complex model. Overfitting might appear because that model is strong enough to approximate everything in the training set, right? So overfitting may happen more often. So it means that variance tend to increase, right? In the case, if you want to make the variance smaller, one idea is to decrease the complexity of the model, right? Use a simpler model. But in that case, it can be harder to train a good model. To approximate the training set, right? Even for a training set, it is harder, right?
So it means that bias tends to increase. So up to now, you already know there's one trade-off, right? There's one trade-off. When we want to reduce the bias or reduce the variance. When we reduce this quantity, the other quantity can increase. This is a traditional view about bias and variance, and it comes from the decomposition, right? And and this view is very classical. So that's why in practice, it suggests that we should have some way to trade off between the complexity of the model and the ability to work with your problem, right? It is just one example. Some algorithm in practice, we can easily see where it can be overfitting, where it can be underfitting. For example, nearest neighbor. Do you remember that? In order to make a prediction, this algorithm will find some closest neighbor and then use the label from those neighbor to make prediction, right? The idea is very simple. Okay, but if we use a lot of neighbors, use a lot of neighbor to make prediction. So in that case, the prediction tends to be very similar. And it means that the variance can be very small, but the error can be high. In the case, if we use very few neighbors to make prediction, then the variance can be high. The training error can be small, but the test error can be very. Okay. So that's why in practice, in order to introduce underfitting, one way is to change to more complex model, but overfitting might appear, right? So in order to reduce overfitting, regularization is needed, right? You should use this technique to reduce or to prevent overfitting, right? Okay. If you want to study more about regularization, you can see from the slide, and we should stop here. Do you have any question up to now? Okay. Otherwise, we can stop here. Okay. See you next week.